Brad Williams, Frugal Finance. This group of continuous compounding sessions, there's 4. Look, there's no easy way around it. It's continuous compounding. It's probably new to you. It's confusing. It's just tough to swallow continuous compounding if it's new to you. With that being said, I'm just forewarning you that the next 4 sessions is going to be a bumpy road. Why? Because it's hard to explain. The best practice is to practice. And with that, I'm going to introduce continuous compounding. And then, I know, do not shut this off, all right? Here, this is purely examples. And I'm going to try to walk you through. It's common sense stuff. It's stuff we've already covered, but I compiled all of this just to practice, to see the different workarounds going forward and backwards with continuous compounding, normal discounting, equivalence, and then a little bit of creativity. I use the word creativity because all you're doing is simple algebra. And then with the simple algebra, you can delve into different combinations. Whether you use these in practice, I can't answer. Why? Because I'm not a fixed income expert. This is going to be used in our derivatives section, and there's a lot of derivatives that we'll be discussing. I know you may not be interested in derivatives, but if this is of interest, continuous compounding, we're going to delve into it. Here we go. Continuous compounding refers to a way of calculating interest where your money grows more frequently, even infinitely. Normally, when you invest money, you earn interest. And then that interest also earns interest. Continuous compounding takes this idea to the extreme, but by dividing time into infinitely small periods. It's continuous. So your money is constantly growing. There's nothing new here. I've introduced this all the way from the very beginning in our future value section. If you took it, if you're just delving into continuous compounding, and this is your first introduction to frugal finance, I suggest perhaps you just take a look at the future value and present value sessions. Imagine investing $2,000 in a fund that gives you 12% annual interest with a continuous compounding. After 5 years, your total would be $36,4420. This calculation is based on a formula that involves a mathematical concept called a limit, where time periods become small, where time periods become really small. Continuous compounding is handy for businesses that handle a lot of transactions. Banks, financial institutions, for example, like daily or hourly, because it reflects how money is constantly being put to work. Convert normal interest rates into continuous ones. You use equations that involve logarithms and exponential functions. We've talked about EXP, and I probably scared the heck out of you earlier using the log normal, all right? But we've been skirting this. We can't skirt it any longer. We're going to have to dive into some of that stuff that may be extremely foreign to you. What do I mean by extremely foreign? Look, we studied algebra, advanced algebra, maybe some calculus long ago. Maybe some of you are new to all this and you're currently studying logarithms, exponential functions. Great. Then I don't have to delve into this. But let's say you're out of college and now you're delving into some derivatives and you're frightened. You're going, I've been assigned to do this, but I'm not an expert. This information might help. For instance, if you have a 10% interest rate compounded quarterly, you can find its continuous equivalent. And there's that word again, equivalent, which is about 9.53%. Conversely, you can find the quarterly equivalent of a continuous rate backwards, forwards, inversion, conversion. These conversions help understand and compare different interest rates more effectively. Here's my suggestion. You take baby steps. You use the formulas that have been pre-prepared. So when I point out a formula, plan to use it. It just makes your life so much easier. Sure, go ahead, brute force it. We all do. Why? Well, because we're not aware of the formulas, or we forgot the formulas, or we think we're smarter than formulas that actually worked. Look, I strongly recommend you doing what you have to do. In the end, most likely you'll come back and you're going to find that equations like this make it really simple. right here, EXP, R to the N. Remember that. That's continuous compounding. Then everything else from there is going to be a branch. So as the frequency of compounding in a year increases, the effective interest rate increases. Since monetary transactions occur daily or hourly in most businesses and money is put to work, where the business of compounding is occurring quite frequently. If one wishes to account explicitly for such rapid compounding, the continuous compounding relation should be used. Continuous compounding means that each year is divided into infinite numbers of interest periods. Mathematically, the single payment compound amount factor under continuous compounding is given by this formula here. So I'm just going to highlight it, put it in bold, where N is the number of years, M is the number of interest periods per year, and R is the nominal annual interest rate. Given P, R, and N, the value of F can be computed using continuous compounding as follows. EXP, R to the N, or EXP, and then this right here is old school stuff. I don't use it. Why? Well, because it makes absolutely no sense to me. Where P of N denotes the continuous compounding single factor. No. So I'm using this F equals P, EXP, R to the N. For example, if 2,000 is invested in a mutual fund earning 12% with continuous compounding, what is the total value after 5 years? We have $2,000. We have 0.21. I don't know what this 21 represents. We have EXP right here, R to the N. So we have EXP1, and then the caret 5, 12. What's 5? Well, we said 5 years, right? And the rate is 12%. The $2,000 is going to grow to 3,644 using continuous compounding. Here is just hard-coded. Here is just Excel. I did the same thing here. I multiply the 2,000 at the end here at the beginning. Same thing. Why do I duplicate it? Just because you can manipulate this stuff. EXP, here's your factor, 1.82. You take $2,000 times 1.82, and you're going to get the same result. For those new to Frugal Finance, I've been preaching this factor. You can compute it in the back of finance books. You're going to see interest rate factors or compounding factors or future value, present value, continuous compounding, annuities, and so on and so forth. If not, you can just take this number here. In the event that your computer system blows up, you can compute this number really quick, and then you just multiply it by your starting number to come up with this number. Okay, effective interest rate with continuous compounding. What does that mean? The effective interest rate under continuous compounding is obtained using the following. I effective equals E to R minus 1. To illustrate, if interest is 12% compounded continuously, then the effective interest rate is given by EXP 12 minus 1 is equal to 12.75. When working with interest rates that are measured with annual, semi-annual, or some other compounding frequency, use the following. M is equal to periods, R is equal to rates. R is equal to M log normal 1 plus R of V, M, thus 12.75 compounded annually is equivalent to 12% compounded continuously. The inverse relationship is therefore 12%. Got it? 12% continuous compounding is equal to 12.75 annual. No, other way around. Sorry. This is continuous compounding on an annual basis. This is 12% equivalent. So the 1275 compounded annually is equivalent to 12% compounded continuously. I just said it backwards. 12% continuous compounding is equivalent to 12.75 annually. Tricky because you're thinking one thing, you're going 12.75% compounded annually is equivalent to 12% compounded continuously. If you take 12% continuous compounding, it equates to 12.75%. The equivalent of 12.75 compounded annually is 12% compounded continuously. Yeah, I know. This is where your thinking just goes haywire. Here it is in big, bold numbers. 10% compounded annually is equivalent to 953 continuous compounding. Semi-annual 10 and a quarter is equivalent to 976. Equivalent yield with continued compounding, 973. How do you know? Here is 10%. All I did was take this number here. Right, let's back up here. We have 1 plus 1 here times 100. All we have here is the value of US 100 at the end of year. So this is what it looks like with continuous compounding. We have 110, semi-annual is 110.25, quarterly is 110.38, 110.47, 110.51, 110.52. All I did was take the interest here. Took the interest, and all I did was subtract the 100. Then I took 1 log normal, 1 plus, and this is the formula for continuous compounding. I just took 1 times log normal 1 plus the 10% divided by 1. Then I took, because it's semi-annual, you take 2, and all I'm using is this log normal formula, which is right here, for conversion. I did this continuously. So continuous compounding for a year, which is 1052, is equivalent to 10%. And we know that by looking at this. We can just reverse it by going 365 times, and all we did is we used this up here, this formula, and here is it reversed. What's this right here? This is just 953. I did some compounding forward, 953, 10, 1025, and I'll get into this later. Continuous equivalent 10, so I took F39, I used F39 and 10%, 1025, 140F. The continuous equivalent verification is 1052, 1052, 1052, 1052. What I did is I went, and I know this is a little early, but I'm compounding forward. We have to find the equivalent verification. And then this is just me scribbling. It's meaningless. You can figure it out, but discounting 5% daily, monthly, quarterly. And this is purely practice. So what I did here is, this is how much you owe at year 3 with quarterly compounding. So what was the example? 2 grand, 50, 50, 50, 50. This is on, let's say $100. How much you owe at year 3. So we went $50 times 1.04. So we have a compounding deal. We went 50 years, compounded quarterly. This is how much you owe at year 3 with quarterly compounding, based on $50. This is how much you owe at year 3 with continuous compounding. All I did was follow the same steps as I did up here. Then I just used EXP. I just hard coded it. So if you want to know what EXP is, it's 2.7182. Generally, it's just 2.7182, and then you just stop there. Instead of using EXP, then I just follow the same steps. Here's the log norm. We're going to look at this 3, 6, 7, 8, 9, etc., to the third times G48 is this number here. What's this 3, 6, 7, 8 to the third? It's probably this inverted. Starting point was $50. Let's see here. I went 1 divided by C47. Yeah. 1 divided by C47, which is this EXP. All I did was invert it in order to come up with our starting number. This is the crazy stuff that you need to figure out. Here's some formulas. 50 times 1 plus, we're using 10% on a quarterly basis. This should be this number right here. 3 years, 10% quarterly. I know. I kind of winged it when I put this together long ago. And then the numbers here, 1 divided by C47 is this number here. And then this is 6.8, 100 by 6.8. There could be some notation here that's not relevant. This is not relevant. But anyway, this right here is just something to work into. Then it's just a matter of practice. We have $100. We're compounding ahead at 10%. This is on an annual deal, semi-annual. This is going to be similar to this right here. It should be the exact same thing. But I just extended this. So I went to 2 years. What's the compounding effect on $100? You see the notation, how it changes? Here's the math right here. Oh, here's the discounting. So we take the same thing, we discount it. Why? Because we need to go backwards and forwards. in order to work through some of the future derivatives. So we have 2 years, 3 years, 5 years. This is all pretty basic finance stuff. Nothing new here. I just packaged it all up into one spreadsheet so I can reference it. So I can share this with you. We have 1 year semi-annual. Notice how it works. Then we have this 2 years. Notice the math. Look at the difference here. How we're doing some multiplication issues. All we're doing in terms of the discounting is we're just dividing this formula, looking at the compounding effect. This is 3 years. What's tricky here is taking into account year 3 and the compounding. You know, because it's compounding, semi-annual, we have to divide the rate by 2. Then we have to use what term? We're using 3 years, but we're using semi-annual compounding. If we go to quarterly, take the rate, divide it by 4, take the number of years, be sure to multiply it times 4. And then if we go into quarterly, up here, we have 4, 10 years, nothing new. So it's pretty straightforward. No magic. In terms of verifying, I just like to verify to make sure that the math is correct. And I clearly screwed up something there. Continuous compounding, we're just going to take the 10%. We're going to come up with this compounding rate. Notice the difference. The compounding annual, or this is quarterly, is 2.685. Continuous compounding is 2.7183. Discounting equivalents, again, use the formulas. What are we doing? I discussed this earlier. The equivalent of 1 year discounted is 90484. Then all I took was J52 times I52 to get 1. And then here, this is just going to be rounding issues. So you probably can just stretch this out and the numbers are going to be a little bit different. Not much. So I probably screwed up something here. 1052, EXP 1 to 1 to semi-annual, quarterly, 1052. It could be really fine-tuned. Let's see here. 418. So there's your equivalent. Notice it's all the same for 1 year. Then 8173, and you need to answer this question. Why is discounting compounding equivalent the same? The answer is kind of odd, but work through it. I'll provide the answer as we move along. The equivalent, 9531, continuous equivalent. What is that? Here, you need to work through the math. It should be the same as up here. You have a discounting equivalent. Don't mix up the two. Discounting equivalent is not the same as compounding equivalent. That's why this rate is the same for this 1 year period. Why? I'll give you an answer later. Then you have the continuous compounding equivalent. Then we have the normal equivalent. So I do this a couple times just for practice. And this is all about the formulas. So all we're doing is take the log normal. Then we're going to take EXP. This is just 10% compounding ahead. And I said earlier, we have this compounding ahead. We're going to delve into this in depth probably in the next sessions. What are you talking about compounding ahead? Well, when we get into forwards and forward rate notes, we have to compound ahead in order to price zero coupons. Get into the practice of trying to understand compounding ahead. I know I haven't discussed it yet, but I will. And then you're going to find the normal discounting. You're going to discount this back. I just put the numbers in here. Go ahead and calculate it if you want. I'm just going to use this formula. And then continuous compounding, 1052, which is this number here. It is constant. And you're going to ask yourself, why? What are we looking at? EXP 10 to the 12th, EXP 1 quarter. Why is this continuous compounding the same? And then why is discounting compound equivalent the same? This is what we're working through. And I want you to just think about it. I'll provide the answer here soon. This is the complexity of continuous compounding and working with derivatives. Brad Williams, Frugal Finance. Yep, we're stepping into the weeds, if you will.